All right. The speaker today is Joel Kamnitzer from McGill, who will talk to us about virtual cactus groups, combinatorics, and topology.
Okay, thank you very much for the invitation. So I'll be telling you about this group and how it arises. Okay, so let me begin with some motivation. So let's take G to be a semi-simple Lie algebra. And V a representation. Then you could study the tensor product of this representation with itself many times. Big tensor product. And this tensor product has an action G, of course, but it also has a commuting action of the symmetric group. And many times this action is pretty interesting. For example, when G is SLN, and this is the standard representation, then you have a Cherval duality story going on. So this is an interesting action of this tensor product. Now, one way to modify this is to switch from the semi-simple Lie algebra to a quantum group. Will be a quantum group. So I'm not really talking about this stuff. It can be a little vague at this point what I mean by quantum group, but it's an algebra over a field, or maybe let's just say over the field of rational functions in Q. And when you set Q equals 1, it's considered setting Q equals 1, you get back G. And it has representations, it's category representations, but just like the one for the original semi-simple Lie algebra. But there's a new feature, which is that if you work with the quantum group, if you have two representations, V1 and V2, there's a interesting isomorphism between their tensor product in one direction and the tensor product in the other direction. So the naive map, V1, little v1 tensor little v2, goes to V1 little v2 tensor v1. This is not a map of V modules. But there is an interesting map, which I'm not going to go into great detail, but it comes from applying a certain element in the quantum group called the universal R matrix. There's some elements in the quantum group tensor the quantum group, or maybe completion of that. And this is a map. This map, this R comes from something in the and this map is interesting for example, has some nice properties. For example, its square is not the identity, unlike this one, which squares the identity. And it satisfies the following condition, which is that if you have a triple tensor product, there's sort of two conditions involving tensor product. Let's say maybe I'll say both. So the first one is that if you want to move this V3 past V1 and V2, you can do it all at once or in two steps. And those give the same result. So either you move it all at once, or after doing some rebracketing, you move it in two steps. Drawing the rebracketings. So this little diagram here commutes. In turn, this diagram implies something called the quantum Yang-Baxter equation, which tells you if you have V1, V2, V3, and you want to switch it completely around to V3, V2, V1, the two ways of doing it are. So here, this we saw an action in symmetric group. Here, we're going to see an action in a different group, like principally because of this fact. So this leads to the rate group. So Vn, it's the rate group. Let me define it first by generators and relations. So it has generators sigma I from 1 to n-1, and relations. Basically, the relations that are satisfied in the symmetric group, except that we don't have the square of the identity. So this relation. And sigma I, sigma j mu, if I mean, they're sufficiently far apart. And this group has a topological realization, which is why it's called grade group, as the fundamental group of endpoints on the space of n distinct points on the complex inverse. From that perspective, you can picture an element of this grade group as a grade. So this generator's sigma I corresponds to a picture like so, which spots the I in hyperspin strand, then sigma I, and a more general element of grade group of grade. Yeah, so this group now acts on such a tensor product. Okay. So the group Vn will act on this V tensor n by UQG module automorphisms. It's like here we have a symmetric group, just naively looking at tensor factors. Here we use this interesting map there, which satisfies the axioms that I said, which leads to the action of the grade group. Now you can do something that you might seem a little silly, but you can consider both this group acting using the grading, and you could add in this naive switching of tensor factors. So like add back what we just got rid of. So take Sn, act on V tensor n by naive switching tensor factors. So you'll lose this. This was nice because it commuted with the G action. This one will not commute with the G action, but you can still consider its action. And together, these two lead to an action of a group called the virtual braid group. So the virtual braid group is defined as follows. It has generators with braid group. It's the amalgamated product of the braid group with the symmetric group. In other words, like a presentation of it will be made by picking generators of braid group, picking generators of symmetric group, and there's some relations. Sorry, question?
Yeah, do you add a sign if we have an n cross symmetric group by switching the tensor? You add a minus sign as well?
No, but
I mean, what is yeah, something that
I don't think there's anything. Yeah, this action is symmetric group is like the same as the other thing. Okay, so in this virtual braid group that has it's the free product of the braid group and the symmetric group with some relations. And the relations are that W sigma I W inverse equals sigma I plus 1 whenever, so this is W here is in the Sn and sigma I are the braid group generators. So this is true whenever of W of this is not it. W is let's say sigma W divide. And this you might think, well, you could imagine this is just true always. That would be like the semi-direct product, but it's not. I only want it sometimes. So whenever W of I plus 1 is equal to W of I plus 1. So in terms of pictures, what this means is you can draw a picture. You have what's called real crossings. This would be a actual crossing, like here's sigma 3, or sorry, 2. And then what's called a virtual crossing. So you just cross without indicating an overline and underline. So this here will be an element of the symmetric group. There's a W in the symmetric group, and it has a property of W of 1 is 3 and W of 2 is 1 and W of 3 is 2, right? So this is like W in the symmetric group, and here's sigma 2. So if you apply this relation, you would get, I think I'm maybe this way, you get W sigma 2. This one is okay because W of 2 is 1 and W of 3 is 2. So W of I plus 1 is W of I plus 1. It satisfies the condition. So W sigma 2, W inverse, will be sigma of 1. So, and pictorially, this means you can slide this actual crossing past this virtual crossing. So this virtual grades, something people have studied in knot theory for a long time. I think it was introduced by Kaufman. I'm not completely sure what the knot theoretic motivations. But you can also study what's called virtual knots, which is the same thing, but where your strands are like.
Joel,
Yeah,
the relations you put in, can you also rephrase them in terms of W being just a simple reflection?
yeah.
Maybe you
So,
don't want to do that, but it's possible to do it.
sorry, not W a single reflection, but it's the same as imposing this condition. So a Rademacher three-like relation. In fact, I mean, the one I drew is this, and this is actually all you need to do. You only need to consider those W's, which are products of SI and SI. Or whatever, you maybe could have a minus one. What I do is have a minus. Yeah. And then, so I didn't exactly say it, but I sort of said it in words, but didn't write it. Maybe that's the thing before that. So together. So let me call this thing the virtual grade group. We call it VBN. And then the statement, which is not hard to prove. I think there was recently a paper that exactly was about this. But, it's not a very nice thing. Is that this virtual braid group acts on this tensor product. Again, where the braid part acts in the interesting way using the R matrix, and the SN part just acts in the stupid way. You know, this relation is easy to check. So we're getting towards our cactus group.
But is this the fundamental proof of some natural phase, maybe?
It's a good question. I don't have a very good answer, so I won't give an answer. But there is a paper of from about 15 years ago, Bartoldi, Enriquez, Eddinghoff, and Rains, in which they constructed the space, in fact, a K/1 space for this group. Maybe you have a different, maybe I have a slightly different answer now, but how to think about it. But
But one
I don't have
way,
any precise statements, so let me not say.
like braids on thickened surfaces rather than braids on thickened on too, right? That's. Do you even think about it topologically always, but. Where the virtual
Say it again?
process where, sorry, I think this can be, this is, I think Kaufman was thinking about it
Yeah.
as braids on thickened surfaces. So because usual braids are like, you have R2 cross an interval, and this is like some G does G surface cross an interval, and then these virtual crossings are if you go two strands cross, but anyway, passing around the hole.
Oh, okay.
So, yeah, that's,
Well, I don't think, well, that's probably a good answer, but I don't think it's related. I wonder if it's related.
no,
Anyway.
I don't think.
Maybe, I don't know. Anyway. This is more motivation for it. The talk's not really about this virtual loop. Here's what the talk's really about. Okay, so given a representation, there will be a representation of maybe G or G perspective. There's a way to construct a purely combinatorial object called a crystal, which encodes it's just a combinatorial object, I'll define it in a second, which encodes a lot of the structure of the representation. So roughly speaking, it's a set which indexes a basis for the representation. As a first approximation, you could say it's a basis. Let me give the formal definition. So G crystal, so instead of a G representation, I say a G crystal. So G is still a semi-simple Lie algebra. So a G crystal is a set B, finite set B, along with some data. The first piece of data is a map from the set to the weight lattice. If you have a basis, which is a weight basis, and talking about the weight decomposition, then every basis vector has a well-defined weight, so it's like that map. And another thing you have in a semi-simple Lie algebra is you have the Chevrolet generators, usually denoted EI and FI. So you want to see how they're acting on the basis. So the second piece of data is partially defined maps. EIs and FIs. But they're only partially defined because sometimes the basis vector might go to 0 under EI. So some partially defined maps. And this satisfies some axioms. I'll just say them in words. So the axioms are that the EI increases the weight by alpha I, you would expect from the algebras, and the EIs and FIs are inverse to each other whenever both of them are gone. So here's an example. So for example, if we take G to be SLN, then we have our irreducible representations are indexed by highest weights lambda, which lambda is a sequence lambda 1 in this case, with a weakly decreasing sequence of integers. Maybe minus those considered up to simultaneous addition by all ones vector. And in particular, maybe we can fix the last guy, I think, is 0. And then there's a crystal associated to it. So the underlying set of the crystal is a set of semi-standard young tableau. So that means a filling of we have lambda as a partition. So you draw it as a Young diagram. Lambda 1 row, lambda 1 box in the first row, lambda 2 boxes in the second row, and so on. And semi-standard Young tableau means a filling of this shape. So it means a filling of the shape which is weakly increasing in the rows and strictly increasing in the columns. Filled with the numbers from 1 to n. And the weight map is just the usual weight of a tableau, just tells you the contents, what the numbers we call it. And then there's some crystal operators, these EIs and FIs, defined on these tableaux. Let me show you an example. So we take, for my example, I take D to be SL3, lambda to be 210, that corresponds to the joint representation of SL3. And then, so I consider a tableau of this shape, 2 boxes in 1 box. And here they are. So I'm kind of arranging them so the kind of according to their weights. Right? Something on the right. This so those are all the 8 semi-standard Young tableau of that shape. And the crystal operators, I'm just going to draw as a sort of a graph. The graph is showing you where this action of these things are. So I'm only going to draw it to the F's because the E's are inverse F's. And so F1 turns 1s into 2s. So it goes like that. Down here, it turns this one into this 2, like so. So. Now, if you've ever studied this representation of SL3 carefully, it's a joint representation, you might be suspicious at this point. Because actually there's no basis. There's no basis you can find for this representation where the Chevrolet generators act exactly according to this picture. It's impossible. Like it's like namely the fault is like lies right here. Like if you let this guy be the image of this guy, then it won't be killed by F1. Not hard to say. So there's like two ways to resolve what I said. One way is to think that this maybe the original approach of fetching bar is to think that this crystal comes from a quantum group representation when you set Q to be 0. So that this is like the 0 temperature limit, this like a crystal. So when Q goes to 0, your maps sort of look like this. So in other words, this is showing you the action of this Chevrolet generator's mod Q. And then there's another approach, which is maybe not very different, but due to Bernstein and Kajdan, which just doesn't use the quantum group, just use representations of G. And in that approach, it's also, these are like the first order approximations in some different sense of the action of the Chevrolet generator. So either way, let me just say that, so it's maybe confusing when we say that in words, so this B you should think of as a basis for V. And then the EI of B, let's say that's the action going on here, your EI of the Chevrolet generator of the algebra. This is equal to like the little EI of B, that's the different basis vector, plus some sort of like lower order terms, higher order terms, whichever way you want to call it. So basically, either way, it's some combinatorial object which approximates your representation. So I think these crystals are very nice, and they have a surprising fact about them. So if you have two crystals, V1, V2, there's a way of forming their tensor product. V1 tensor V2. So as a set, this is just V1 cross V2. And the weight map is just component-wise addition. The hard part is to figure out what you should do if you want to apply. I'll write the little tensor, but this little tensor just means there. So what to do if you want to apply this EI to some tensor product? Either has to go. You would like to put it's this. You would like it to be the sum of the two things because that's what it is in the representation. But you can't put a sum. We're just going to define it set. So it's this or this. And there's some rule which I won't bother writing down. But there's a rule which actually has a nice picture associated to it. You know, just draw the picture and leave it at that. This picture tells you where you should, which way this EI. So EI is like going on this over here and over here, and you look at this set down here is the. So this thing down here is V1 plus V2. And you look down here and you see which way in this example is that you go this to act, so you act on the second vector. And the way you do it is you make this funny picture where you take the two strings here and then turn them into this funny picture. Anyway, so there's some purely combinatorial rule which tells you what is this, and this is manifestly not very symmetric in the two factors, as you see from the picture here. Very unsymmetric. This line, very symmetric. So it's some time ago, with Andre Henriquez, we defined an isomorphism between the tensor product in one direction and the tensor product in the other direction. So there exists an isomorphism, which can be defined in like a not that straightforward way, analogous to R matrix, but not directly really related to R matrix, but analogous to that R matrix, somewhat related to that R matrix, between the tensor product one way and the tensor product in the other direction. And this isomorphism has some interesting properties that are analogous to, but different from the ones that you see in the quantum group. So first of all, it does square to the identity, which might lead you to think it's kind of very trivial, but it doesn't satisfy the property that I mentioned for the R matrix isomorphism. So if you switch B3 quickly past B1 and B2, or if you switch them slowly past B1 and B2, this was not commutative. So because of that, you get an action of a very interesting group. I think it's interesting on such tensor products. So this is cactus group. So the cactus group so it has generators, I'll call it Cn. It has generators Sij, where I and j are between 1 and n. One is smaller than the other. Which you should think of as being associated. You should think of the points 1 up to n, the numbers 1 up to n. And you should think of this generator as being associated to an interval inside of this sequence of integers. The relations in this cactus group are that all the generators square to the identity, and that if you have two intervals which are disjoint, the generators commute. It's kind of like in the break group. And if you have one generator, one interval, this is unlike what's going on in the break group. If you have one interval containing the other interval, inside a smaller interval, KL, then the outer interval will conjugate the inner interval. So this will be S I J, and the what you get is what you get by flipping this inner interval inside of the outer interval. I plus J minus L. I plus J minus K. So that's the definition of this. And then the theorem. So this is from a long time ago with Andre Henriquez. Is that it's a principle. Then this cactus group acts on n full tensor product. And just like this acts as automorphisms of the crystal. So just like in the quantum group case, that isomorphism we thought was an isomorphism of representations. This is with sigma is an isomorphism of crystals, and this guy I can by automorphism. It might not be super obvious at this point how these generators act, because only the ones like if it's I plus 1, I and I plus 1, then it just acts by permitting the neighboring factors. A general element Ij acts in the following way. I'll maybe say it in words, but you take your section, you take your tensor product, take the I and j factors, and you want to completely flip these around. So completely reverse their order. And any way you do it will be equal as long as you are always do it in like the minimum number of steps. So you take the first guy and like move it past the rest of the guys. And then take in this next section, take the first guy of that and the rest of them move it past. So if you do that, actually it takes like n, whatever, j minus I steps. Any way of doing it with j minus I steps are all equal as a consequence of some axiom which I didn't write down, and that's the actually this section. This is some other way of thinking about it, which makes it look a bit more natural. This description makes it look a little bit weird, but that's actually this SIJ, and that's this this cactus reduction. Any question about that?
Kind of like considering these like longest elements and some segments, and then
Yeah. So
something funny
this
happens.
cactus group has a, in a similar way, you can define the cactus group of any vial group. So it's any vial group, it has generators labeled by connected subdiagrams of the Dickin diagram. And they correspond, the cactus group would always map to the vial group. And those generators will map to the longest elements of those sub-vial groups. So this cactus group, I should have said that. Here. This cactus group maps to the symmetric group. And the map takes Sij to the permutation, which again completely reverses the is the longest element on the group of the subgroup like involving the identities. That's second. Okay, so now we're ready for the main player of the day, the virtual cactus group.
You didn't know how to present the pure cactus group?
Sorry?
You didn't know how to present the pure cactus group?
Uh,
Kernel of that.
no. But it will be known, and I can explain. Maybe I won't explain, but it is known how to present the pure virtual cactus group.
Okay.
Yeah. The kernel of that map is called the pure cactus group, and I don't even know a set of generators. The closest thing is I can tell you is a set of elements whose conjugates generate the group.
Okay, that's a question here.
Yeah.
So the crystal should be thought of as like the highest, somewhat highest order component thing. Is that, it's like a rigorous statement that's like true for any choice of crystal? Or is it just sort of like?
Well, here, so what's pretty amazing is that there's an say you have B, some representation of G. To answer your question, let me just go close on this. Say you have some representation of G, and then there's a notion of a basis. It's called from a perfect basis, which just means that it's like well adapted to study the action of those EIs and FIs. And this thing produces, when B is a perfect basis, then B has the structure of a crystal. So just take B as a finite set, and then you only remember the like leading order behavior of EIs and FIs. And the theorem is that this crystal doesn't depend. If you pick a different basis, perfect basis, then you get the same crystal. In fact, it's a unique isomorphism of these here. But yeah, you get an isomorphic crystal if you pick a different base. So now the way the crystals sort of like canonically associated with the representation. Maybe you ask the opposite question. You ask, given any crystal, does it necessarily come from a representation? And that's a more subtle question. It is, but only if you add like some additional axioms to the notion of crystal, which is more than the ones I said out loud. And they're not very pleasant. So it's not a great characterization. For example, like you put if you take a joint representation of SL3, but sort of collapse the two central dots to a single dot. So you have this set of 7 elements. It's not the crystal of any representation. This would not be the weight diagram of an SL3 representation, but it still satisfies the axioms of the crystal, at least the axioms that I said. And interestingly enough, these bad crystals, they don't This isomorphism between the tensor product, it only exists for the good crystals, not for the bad. So now I'm gonna do what I said, what we did with going from the braid group to the virtual braid group. So the natural thing to do now is to take this crystal tensor product and add in also just naive permutation of tensor factors. And then ask yourself what relation this has between this SN and that vector group. So then you get this virtual cactus. So the virtual cactus group is the group with generators, is the free product of the cactus group and the symmetric group with some relation. And so it's going to be like before, sometimes a symmetric group element will conjugate a cactus group element. When it does, it always conjugates it like this, but it doesn't always conjugate it. So this happens if, whenever, W of I plus K is equal to W of I plus K for all K from 1 up to J minus 10. So I like to say that this condition is that W is linear on the interval IJ.
More like Wi-Fi.
So in a picture, I usually try to picture the element of the cactus group like so. So I think of it, so this would be an element of the cactus group S13. So what I picture is that I take like a normal sort of strands coming here, I cut out my plane here, I cut a circle out and I glue the opposite points. Which is like amounts to gluing like a RP2 or something bracket. But you could say just cut out a circle and glue opposite points. So this strand is kind of connected to this strand. So I picture that as a connected group element. And then here I might have some symmetric group element, which permeates this like this. I can draw it like that, and then I can slide this blob, this RP2 past this thing. So. That's a picture of the village. Okay. So the upshot of this was the easy result is that this virtual cactus group will now act not by crystal automorphism, but this act as a set on the tensor product of the crystal. Okay, so that's about combinatorics and about the groups. Now about topology. Any questions? We're saying, but this virtual cactus group maps to the symmetric group, where we use the map to the from the usual map to the cactus group, symmetric group, and the identity map from the symmetric group to the symmetric group. So these relations hold for their images as well defined map. And yes, the kernel of this is called the pure virtual cactus group. And I won't give the presentation, but it does have a pretty manageable presentation. Similarly, the pure virtual braid group also has a pretty simple presentation. I mean, even simpler than this. Not surprising. Like the number of generators is fairly large. It's n factorial divided by n minus k factorial. See what generators is? The sum over all k of n factorial over n minus k factorial. Quite a few generators. But it's so nice. Okay. So first, let's discuss how the cactus group occurs as a fundamental group. So, so for that, we need some concepts from algebraic geometry. So, this, I'll call it a cactus curve. So just the name I just remembered. This 0 algebraic curve with sort of similarities. And mark points. So what does this mean? So it means our curve has a bunch of and one more condition, which is that the trivial automotive. So our curve has a bunch of components. Every component is isomorphic to P1. So it's a bunch of P1s. The picture of how they meet is misleading because I actually do it in a nodal singularity, so they actually meet like this. And there's a bunch of marked points. Some marked points and also these double points. And every component has at least 3 marked points or double points, otherwise there would be non-trivial automotives. And there's a total of n marked. Okay. And there's a moduli space of these curves. So it's a special case of this Lee-Mumford moduli space where in general you might have curves of arbitrary genus. So this one where you just have genus 0 is very combinatorially tractable. So this is this moduli space. Lee-Mumford moduli space of cactus curves. For example, if you take n equals 3, so we have 4 mark points, then you just get a P1. So it turns out that using the automorphisms of P1, you can bring the first 3 mark points to any specific spot, which we'll call it 0, 1, and infinity. And then you have another mark point, which is running around and can be anywhere, and that defines the element of P1 under this isomorphism. It could sort of coincide with this, but then they go off on the and so it's called the cactus curve, is it? I'm making this cactus, and that's why the group is called the cactus group. So the theorem. Yeah. This and David's is that the equivariant fundamental group of the real locus of this moduli space. So now I take the real locus, which means effectively means I just look at real curves, marked points which are real defined over R. This fundamental group is isomorphic to the cactus group. And moreover, this space is actually is actually a K-pi1 space with groups. All the higher homotopy groups match. The idea of this isomorphism is as follows. So you pick a base point, which is corresponds to a generic sort of point. So you have n+1 marked points, which are all distinct, and they all live on the same. Well, they're obviously distinct, but they only live on one. Now, a group of these marked points decides to start coming closer together. So all the marked points between I and j decide to start coming closer together. That defines like a path in the moduli space. They move closer and closer together. And you reach a special point, or not that special point, but you reach a point in a codimension point that lives in a codimension 1 stratum in the moduli space where they've gone off onto their own components. So here's a 2-component curve where I and j are off on their own component. Sorry, not just I and j, but all the things between I and j are off on their own component. Now the other ones are. stack on the main component. And once they do this, this point has actually is the same because this P1 has its own automorphisms independent of this one. You can flip the order of these points around without affecting the order here. And it's the same point as the one where they're in the opposite order, and then they come back onto a different part of the open locus, but now in the opposite order. And so in this way, elements of the element Sij of the cactus group corresponds to this path from here to here. So it's a path between 2 points because it's not really this equivariant fundamental group. So it's like after up to this Sn actually you've kind of gone back where you are. Okay. Okay, so the main thing I'm going to answer today is like what space has a what's the classifying space for the virtual cactus group? And the answer turns out to be kind of nice. Think so? So begin with the following space. So begin with the line. So those are cactus curves. Now my next notion is called a flower curve. So what's a flower curve? It's an algebraic curve again. So it's a curve, C, and it has maybe some components, or as well as C1 to Cm, and each Cj is isomorphic to P1, and all these points meet in one single point. So the intersection, every Ci and Cj intersect, and at some particular point, which is the common point of intersection of every one of these. So they kind of look like a flower because they all pass through the same point. Actually, again, the point is the picture is misleading because something which I won't write down is in the neighborhood of this point Z0. It looks like the intersection of the coordinate axes in Cn. So they don't look like this at all. They look like this. So that's the intersection of like the coordinate axes in Cn. And they carry some marked points. C carries and non-distinct marked points. Not necessarily distinct marked points. And also I fix a non-zero tangent vector in the tangent space at this special point in every curve. That's the data. So again, we consider these things, we only pick ones that have no automorphisms, and then we consider these things up to isomorphism. And that defines a moduli space, which I call yn bar, the moduli space of these curves, which I call flower curves. So let's examine the structure of this moduli space a little bit. So imagine we just had one of these things are called petals. Imagine we just had one petal. So I have one petal. I still have a special point on it because I still have this tangent vector. So I have this tangent vector, and then I have some points which are not necessarily distinct. And I don't have any other things going on because these are only one guy. And these are considered up to the automorphisms, but because I have this tangent vector, and this special point that really reduced my automorphisms from PGL2 just to the additive group. So I just have n points on C modulo translation. So this part of the moduli space is the y-ends. This is one petal. So this is the generic situation. You know, one petal, and this is just Cn mod C. So this space is a compactification of just this vector space in mod C. And there's actually a general procedure for compactifying a vector space with a hyperplane arrangement. Due to recently being a lot of work on it, originally invented by Ardila and Blucher, and call it to the name Matroid Schubert variety. And they're recently studied a lot by June Ha, McCraw, Botan Lang, many other people. And so this thing called Matroid. So this YN bar is the Matroid Schubert variety. Of the type A hyperplane arrangement, also known as weight arrangement. Type A. By time I'll come back to this later, but also another thing is that this space we looked at before this, this also sort of canonically produced from the same root hyperplane region. It's actually the decontinued Pachesi compactification of the same root. So there's sort of come out two procedures for producing spaces from hyperplane arrangements, and this one of them is Yeah.
Is it possible to say, in 5 words or less, what you add when you take the this Matroid variety? So what is it?
I mean, in this example, you add all these curves of other petals, which is basically some union of other products and things like this. In general, something like that. Yeah. You add a bunch of different vector spaces of smaller dimensions.
And they're labeled, the original components are labeled, they're combinatorics naturally labeled as some combinatorial thing.
The irreducible components of the boundary.
Yeah.
The strata of the boundary, let's say, are labeled by what's called the flats of the arrangement, so all the intersections of all the points. The components of the boundary, that's what people like. Okay, so this is not quite our space that we're looking for, but it's closely connected. So in fact, if you're paying close attention, you might have said that there's some thing. Okay, let me okay, so cactus flower curve. Well, it's what you might expect combines both notions. So a cactus flower curve is C, which is such a sequence of curves. And it's basically everything there is the case still, but now each CJ is not a P1, but itself a cactus curve. So it carrying distinct mark points, but still carrying this tangent, but still the components, these guys all meet in one point, and still we have the tangent vectors. So it looks something like this. So I have this special point Z0 here. There's some other mark points like this. There's some mark points on this guy. There's some mark points here. And then the data of this tangent vectors in the middle. So that's a cactus flower curve. And the mark points are now distinct. And then that FN bar is this. Vectors. And so it's a space which combines somehow both ideas of and so this theorem. So we take the real locus of this cactus flower space, then it's equivariant fundamental group is isomorphic to the virtual. So. So this is with, I'm gonna go get all the co-authors here. So. Alex Eden. Myself. Let's get it in the right order. You and me. Piotr Przydzycki. I apologize to him for misspelling his name. And Lena. So, this, what am I gonna say? Oh, and moreover, the space is again, as before, K-pi1 space for this group. How much more time do I have? None, or-
Like 5-10 minutes.
Okay. Maybe I'll just say very briefly, that, the idea of the proof of the theorem is kind of interesting, I think, is that we realize this group, sorry, this space, as combinatorially. So the idea is to realize this kind of combinatorially as a cubical complex. So that's a little bit hard to explain what this means exactly, but I can explain a variant of it, which is much easier to understand. So this space of cactus flower curves maps to just the space of flower curves. The fibers, this map collapses all these cacti here, so all these things will go to a single, you collapse all this and you get the mark point with time explicit here and stuff. That's this map. The fibers of it are indeed products of Boolean morphic spaces. I mean, generically, it's an isomorphism, but the exceptional fibers are products of Boolean morphic spaces. And this thing also has a combinatorial realization, which was actually found many years ago by this Beer paper that I mentioned here, Bartoldi, Eringhoff, Enriquez, and Reins. And the realization is as follows: this is isomorphic to, you take the permutahedron. So that's the polytope you get by taking the SN orbit of some points in Rn and taking the convex hull, and then you mono by all parallel faces. So any two faces which are parallel, you identify them. For example, you identify all the vertices together. If when n is 3, you have a hexagon, you identify the parallel sides, but then you even go a step further. And if you just did that, you would have a torus, and you would have two vertices. But then you identify all the vertices too, which are there only two of that. You get a torus with 2 points identified. So this is what I mean by a kind of combinatorial realization of this space, and we somehow we do something similar and make a combinatorial realization of this Fn bar. And that's what it's just there. I'll stop there. Spins.
Oh, you said that this is, and even for the non-virtual chemistry, you had like a K-pi1. I was wondering, is there anything learned about like the cohomology of these groups, and they're quite closely related to breaking, so is there some like stability in the cohomology as well?
Stability in the cohomology, I don't know. Cohomology, yes, we actually a long time ago wrote a paper with under Enriquez, Eringhoff, and Reins about the cohomology of this, like of the cactus group, so equivalent of this K-pi1 space. We gave a kind of operatic description of that cohomology, and there were some conjectures left open, which were, and there were fairly recently proven it was a Barashkin and Wilbacher. But I don't remember a super amount of details about that, and I don't know anything about the cohomology of these spaces. And this might be more difficult because these spaces are singular, unlike the MN plus 2 bar. And I don't know anything about stabilization. Stabilization in the sense of this like representation stability or it's.
Yeah, yeah.
What do you mean by it? But maybe people have said it, basically,
The great question, does your approach, in some sense, mimic as best as possible as the Davis and company approach, or does it, or you know, on the other hand, does it give it a new point of view on their own? Does it give it maybe, does it suggest an alternative group of their result for the cactus case, or maybe not very long?
sort of. But basically not, basically it's kind of the similar, like, their approach is I mean, their thing works a bit more generally, they actually work with any users. Deconchaining adjacent conducting mutations. And their approach is to work with cubical complexes. And to do something mimicking blow-ups for the cubical complex. So, this space here, this cactus flower space is like sort of like a blow up of this flower space along this places where you have these mark points coinciding. But because of the singularities of our situation, it seems difficult to actually make that as a rigorous statement. So I don't know how to use like precisely their blow up technology to get this result. So we kind of did by hand in some sense without their blow up technology. So just directly making this estimate. Yeah.
Can you repeat again why N is CN on C?
The open locus?
Yeah.
So I have a curve. So I have a curve here with one petal. It has some mark points on it. So I consider that up to automorphism. So what I have is I have P1 to the I have Z1 Zn, which all is in P1 to the n. And then I have another point Z0, which also lives in P1, which is not equal to any of the others. I don't really see this. These mark points are not allowed to coincide with this special point. And I have a tangent vector there, which is not 0. So I consider all of this modulo the action of PGL2. Because that's the automorphism group of P1. Now, the very first thing I do with this PGL2 is I make this point be infinity. 0. So I make this point be infinity. So it goes away from the data, and then I just have Z1, Zn in Cn. And I have also this tangent vector, which is now a vector of infinity. And I consider this up to the stabilizer of infinity in PL2, which is just the Borel of PGL2 upper tangent matrices. And then I make this non-zero tangent vector equal to 1. And then I reduce my group to just C. And then yeah, it wasn't really clear from my previous explanation. Yeah. So I can regard this space as being kind of compactification of CN1C, and this space is like, if I did the same thing here and I looked at curves of just one petal and one component in that petal, well, the points would have to be distinct. Still the same condition. So this thing to sort of compactify Cn minus diagonal.
I think Joel again.
Maybe one last question. Is there some significance of this, was it virtual braid group action on tensor powers and vector representation? Is there an analog of the Schur algebra for this?
Not that I know of. I don't know, people don't seem to study this thing, I don't know what, but one thing that's like bad about it is that it doesn't commute with the G action, so. Like normally you have a commuting action of the braid group to the quantum group, but here it's not commuting with the quantum group, it's only preserving weight spaces, so it's like maybe not a very interesting thing.
But what about action those two? will do that, right?
Yeah.
It's still they're useful, so.
Yeah, good, yeah. As I said, I did recently see a paper exactly about this stuff, about this virtual break group action. I forgot who was back. There was a reason to about it. Maybe I should very well. You might have what's the connection between topology here and the combinatorics in the beginning. Well, no one asked that, but
Yeah, you get a local system.
the answer, maybe you already know, at least some people in the audience already know. But for the original cactus group, the connection is provided by this work of myself and Brenda and Eva and Alex Weeks. So we proved that there's a natural way to build a family over the moduli space. So the monodromy of that family recovers the monodromy of the covering space over the moduli space. So the monodromy recovers the cactus group action on crystals, and the way we did it was by constructing these Gaussian algebras and considering monodromy, considering eigenvectors to these algebras. Anyway. And there's a similar story in progress. The reason why I mentioned that there's a similar story in progress for these for this action for these spaces.
That's for you, yeah.
It's actually sort of this inhomogeneous Gaussian algebra. It's sort of like the dual how dual something to its means. You can have
How do the two copies, I mean, you can say roughly, how do the two copies of arrive in this?
What about two copies? I mean,
Well, you have BN and SN, right? And you said,
protected group and that's
well, we're starting in the crystal limit.
well. I don't think they really rise. I mean, they only rise because they rise in this fundamental. I mean, they rise in this fundamental group and they rise in the reaction of the crystal.
Well, maybe I can rephrase, I mean, at least morally, this should be a crystal limit of some qubit germ, right?
Yeah.
And,
Ah,
but maybe that's what you're saying, maybe that is. No,
maybe Lena has a better answer than you. You mean something like you had some KZ kind of thing where you.
so the KZ would account for the break group. Of the
Yeah, so some version of KZ where you account for both things.
And then you're putting in some additional symmetric group, or, but maybe it's not sense, it's staying on the line symmetric group.
How do you mean?
So this would be a KZ maybe on 10 times the same vertical, no, not necessarily. Not necessarily, okay. Oh, yeah, but not necessarily.
Well, we can talk about it after maybe. Okay.
All right, thanks. Thank you, Joel.